Thanks. So yeah, as you heard with my talk, we're going to get back to Lunar, about which you already heard on Monday, but I'm going to focus more on what we at the Microgravity User Support Center at DLR Cologne are doing to support teams that want to test instruments and operations within Lunar. So to get everybody on the same page, Lunar is a collaborative project by DLR and ESA in Cologne. The heart of Lunar is the main hall with regolith, which has a size of 700 square meters. And as you can see, these are no longer artist conceptions, but actual photographs. So it's really happening. We will have an area where the regolith goes up to 3-meter depth. That's what you can see here in the construction drawing, and also in the fenced off parts that you see in the photograph. And we're going to open this year. There will be quite a few different elements in Lunar. Not all of them will be available directly after opening, but they will be more added subsequently during the coming years. Some of them are the sun simulator, which will allow for different illumination conditions and to see how they affect both robotic and human vision. Then the gravity offloading to lunar gravity. And for the astronauts, also suits, as on the one hand, to protect against the dust of the regular simulant, but also to simulate the limited mobility. And in coordination with that, some medical system that will be developed by the Institute for Aerospace Medicine. We will have a ramp with an adjustable slope of up to 50 degrees to test traveling up slopes, a mock-up of the Argonaut lander, at some point a full-size robotic rover. And then the thing that we are mainly involved in is the deep floor area, where we have this 3-meter of regolith depth that you can use to build more topography, but there will also be limited thermal control. And you can test subsurface activities like drilling or sampling. And we will also bury some exploration targets there. While we won't have the huge rover from the beginning, we do have 2 smaller rovers that are based on 3U CubeSat size. There's 2.5U left for instrumentation in that, and they can be used by people who just want to test one specific small instrument and don't have the mobility platform. And in coordination with that, we'll also have a ground segment and test adapter that will help if you don't have the full capacity to integrate with the operation system. So we heard a little about seismology. So yesterday about the Apollo data, but we also heard that there was a seismological experiment on the Chandrayaan-3 mission. And there's upcoming experiments like the far-side seismic suit and also the LEMS deployed instruments on our Artemis 3. So in preparation for that, we will have a reference seismological station in here for people who want to test seismic equipment. And also we will bury 500 meters of distributed acoustic sensing cable all across the hall. And then, of course, there's also the ground segment with experience and operation of experiments, rovers, and landers, and which will allow for end-to-end testing. So I want to tell a little bit more about the physical properties of the regular simulant that we are using. It's a Mara simulant from a nearby quarry and basically mechanical crushed basanite. We will need 900 tons to actually fill Lunar, so it's available in huge quantities. And for the grain size distribution, as you can see here, so the red dotted dashed lines are from Apollo lunar soil samples. The blue curve is actually what was published for initial sample in 2020, and the green curve is a more recent measurement. So you can see that there's some variability, and that's what we also get from EAC, so that probably there was some changes in the batch composition between, and we'll have to look in that more carefully. We also have quality control by the quarry, which are these gray crosses, but they are just using dry sieving, so they probably use all of the small size particles below about 150 microns, so you can see there's a strong deviation there. So what we try to do for characterization is we work together with the Technical University in Kaiserslautern to get elastic moduli and seismic velocities. So in the top, you can see the Young's modulus and shear modulus for 2 different densities. So that's why you have these 2 different colors. Under different pressures. So the red bar is the overburden pressure range that you will have in Lunar. So that's basically the first 3 dots. And we also have from that the seismic velocities, so P-wave velocities at the bottom left and S-wave velocities at the bottom right. The gray line, the vertical line there is what's been measured on the moon in the uppermost like 3 meters of regolith, and also at the corresponding pressures. So you can see that the P-wave velocity is actually quite good in the lunar range. The S-wave velocity seems to be a bit large. And we also see from the difference with overburden pressure and also the difference for different densities that compaction will definitely induce a velocity gradient. During this research, they also measured the thermal damping, and the Q is 30 to 40. And we know that on the moon, it's much larger, but that's due to the total absence of moisture on the moon. That's just something that we cannot simulate because we will have atmospheric moisture in Luna. We also did some tests at TU Dresden on the electric permittivity with different overburden pressure. Again, the red line is the range in Luna. Yeah, some of these, so this pinkish curve corresponds well to already published measurements. We also did first test with the soil moisture sensor that we're going to use, and it gives quite similar results. So you can see here the data from 2 sensors against time. When first we had them in air, where we got a value of 1, which is what you expect. Then right in this regolith simulant at about 5 centimeter depth. So that would be very shallow overburden pressure, and you get a value of 3.5, which is also what you get from the measurements at Dresden. And then if you add water, of course, the permittivity goes up. And this is the range that was measured on lunar samples. So we can see that for low overburden pressures, we are also quite well in the range that's measured on the moon. Finally, DLR Berlin, the Institute of Planetary Research, did some thermal characterization, measuring thermal conductivity at different temperatures. So this is at minus 55 degrees centigrade to plus 25 degrees centigrade. There's a small different variation with temperature, but a much larger variation with compaction. And the values are, however, all 2 orders of magnitude larger than on the moon, and that's because we don't have any vacuum. So the heat transfer through the air within the simulant has a very huge effect. However, these values were already used for simulation. If you try to heat and cool the regolith in Luna from the surface with liquid nitrogen or heating rods. So in the background here, you can see a figure that's from the paper by Hein et al. Using diviner data, which shows the variability of temperature in the subsurface of the moon against time. And the curves with the dots are the simulations. You can see that on the moon, basically, the diurnal temperature variation stops at about 20 to 30 centimeter steps, whereas here, and also equilibrates at around 260 Kelvin, whereas here we equilibrate at about room temperature, but at about 50 centimeter depth. So we basically have also no propagation of temperature changes below. Then something about the instrumentation that we want to put in the deep floor area. We want to do some monitoring there. So we will have temperature sensors on each of the sides, and also some mixed moisture temperature sensors as shown here that are continuously recording. We also have some things that will not be continuously recording. So we got from DLR in Berlin a spare inside HP cube tether, which basically has 14 temperature sensors about along a depth of 450 centimeters. So we will bury that. Of course, only 3 meters of that because we only have 3 meter depth, but then we'll get temperature versus depth curve. We will have thermal conductivity sensors as shown here. And we also have, as I already mentioned, the distributed acoustic sensing fibers throughout Luna. Then exploration targets. So it's really not easy to see on the slide here on the big screen, but we have these 2 different slopes and the 3 meter depths of the regolith in this area. And this is already an exploration target in itself. For GPR calibration, we'll have this triangle that's shown here, and also a sphere. And we will try to simulate a lava tunnel because that's one of the targets that's interesting for exploration. And we'll also try to simulate water ice. So we cannot put actual ice in there because we have no way to freeze all of this. And we don't want any water to get into the regolith because it affects the mechanical properties very strongly. We will use one massive disk to simulate a water ice layer, like the baseline that we have to be able to resolve. And then also something that's more like trying to simulate a cryostructure that you can see in permafrost on Earth with an L-cross percentage of ice simulant within the regolith. Finally, I want to talk a bit about reference measurements. So one thing was we wanted to know what exactly is below the hull, because maybe some of the instrumentation can actually look below the floor of the hull, and that's what we did. Some seismic measurements. So we did some refraction lines where you can get P-wave velocity and depth of the layers directly from the data. We also did some array measurements where you get a Rayleigh wave dispersion curve is shown here, and also HRV spectral ratios, inverting all of that together. We get these kind of velocity models for P and S waves, and some interpretation based also on available borehole data, where we know that the uppermost 15 meters below are sand and gravel, and then below that you get clay, and also the groundwater table, which explains why the P velocities have a much larger jump here than the S wave velocity. So that's due to the groundwater. And then at about 180 to 190 meter depths, we get to the bedrock. We also wanted to know if people want to test seismic equipment about the background seismic wave field. So that's interesting because I don't know if you can see it, there should be a red dot somewhere here, which is the location of Lunar. And you have these two circles here. And you can see we are right next to the international airport. And also we have a lot of equipment on campus that's doing that. So I will go a bit faster. We looked at power density spectra. This is a new high noise model and it's a new low noise model. And basically above 1 hertz, we are above that because we have a lot of noise from man-made sources, and that's kind of shown here for 2 hours of data. Then you have the spectrogram below, and you have these horizontal lines that are machines. You have the transient signals that if they have main energy between 10 and 30 hertz are cars. If they have main energy above 50 hertz are airplanes. And you also get these Doppler shifted signals here that are in this case from helicopters flying over the station. And then we also get some specific signals like here in this 200 seconds window, which is, for example, the wind tunnel. However, we can actually see events, especially during late in the evening. And this is a really small earthquake, which happened very close, but you can see 3-component data and PNS waves. And we're also good at teleseismic frequencies, where you can see in blue the data that we recorded here compared to a permanent station that's on the bedrock. And you can basically do a wiggle-to-wiggle comparison, except here where you have some strong influence of scattering and amplification directly up to the P wave due to the sediments. We also did last week a GPR measurement, again with Theo Drayson, to characterize the reflections from the floor. And yeah, so regular delivery started this week on Tuesday. So you can see the first big bags here on this picture. And you can also see we need a lot more to actually fill all of this. And so, yeah, I leave you with this outlook, and you can look at the web page and also sign up to a newsletter if you're interested. And you can also talk to me if you want to know more. Thank you.
All right, thank you very much, Brigitte. That was wonderful. Do we have any questions from the floor? We've got time for 1 or maybe 2 if people are interested. I just covered all the information you could possibly ever need, and everybody's going to email and find out more.